In example 1, I want to graph the function f of x is equal to the absolute value of x. So we'll get some practice using function notation. And then once we get the graph, then we can use that to determine the domain and range. So you could still use a table of values if you want to call it y is equal to the absolute value of x. But again, I'm just practicing with function notation. I'm just going to plug some values into it, like f of -3. Using function notation, every place you see an x, you just put that value. So that's the absolute value of -3. And the absolute value makes this +3. So this is the same thing as saying, if we have f of -3 is equal to 3, we also have the point -3, comma 3. So these two things mean the exact same thing. So okay, at -1, 2, 3, I go up 3 places, so I get a point there. Maybe I'll go from -3 to +3, and that's probably going to be enough. So let's see, f of -2. Well, I know that's going to be the absolute value of -2, which is just +2. Or, said another way, that's -2, comma 2. Those are the same thing. So let's see, we get -2 up to this spot here. F of -1 is the absolute value of -1, which is +1. And this is the same thing as saying the point -1, 1. So we have -1, 1. And one more here. All right, what about f of 0? That's the absolute value of 0. And the distance from 0 to 0 is 0. So this is 0, comma 0 as our point. If we want to try one more value, maybe we could go to +1. And the second that you see a pattern, you really don't have to continue. So if we check x is equal to 1, that's the absolute value of 1, which since 1 is positive, it just remains 1. This is the point 1, comma 1. And we get this spot here. So we're just going to get like this mirror image of the points that we just found. So we should have 2, comma 2. 3, comma 3. In fact, we're going to get 4, comma 4, 5, comma 5, and we get the same points over here. This is probably more than you needed, but the pattern is we get this linear part of the graph going this way, and then its reflection over here. So this is a pretty decent sketch of the graph, just using a few points and then going from there. If you want to start with the domain, so that's all of the x values that appear on this function. It's definitely a function. I think it's going to be all real numbers. That's from -infinity to +infinity. No matter what spot that you choose on your graph, you will get everything for the x-axis back. So like you get this spot over here, look down to the x-axis, that's this location here. As this point travels along the curve, it's tracing out every number on the x-axis, which is why the domain is going to be all real numbers. But the range won't be all real numbers. If you look at the graph, let's see, if you choose maybe this point again here, and you look over to the y-axis, you get this positive y value here. If you choose, this spot on the graph, and you look over to the y-axis, you get this location here. But if you check a negative y value, like -2, and you look to the left and you look to the right, you actually don't meet the graph at any single point. So there are no negative values in the range of this function. They all start at 0 and then move up towards +infinity. So the range is 0 to infinity. And we're just determining that by using the graph. So we used a few points in our function, we plotted them, we sketched the graph and around it, and then once you have the graph, you can answer a few questions about domain and range. For example 2, we want to graph the relation the absolute value of y is equal to 2, and then from this determine if this is a function or not. Like, can you take this equation and write f of x is equal to your formula calling this thing a function? Is that possible? So maybe a good place to start here is to think of points that make the relationship between the absolute value of y and 2 true. So I'll write that over here. The absolute value of y is equal to 2. So all you need to do is think of points that make this expression true. So maybe the most obvious one I can think of is if you choose 0 for x and you choose 2 for y, and you substitute that into our relation, that's the absolute value of 2, because I'm putting 2 in place of y, is equal to 2. And well, yeah, 2 is equal to 2. This is definitely true. So this point of 0, 2 works. So I'll place that right here. And then maybe if you look at this a little bit further, there was nothing special about 0. I mean, you could put 1, 2, 3, 4, -1, -2, -3, -4 in place of that spot. And this portion would always be true. It's the 2 that makes this important. So you should have the point 1, 2 and 2, 2, -1, 2, and so on. In fact, you get all of these points going in this direction here. But there's more, because here we have the absolute value. So I chose 2, but thinking about it a little bit, if you were to put a -2 in place of y, the absolute value of -2 is +2. So I'm going to check 0, -2. Does this point work as well? In place of y, I put -2, and I'm asking if that's equal to +2, and it is. 2 is 2. So this one actually gives you this other point as well. So that's at 0, -2. And again, the 0, not really important. I could have said 1 or 5 or 18. So you could have 1, 2, 3 for x. In fact, you get all of these values going in this direction. And you get all of the negatives as well. So this graph is now the relation, the absolute value of y is equal to 2. You get two pieces. One's located at +2 and another at -2. The domain, just by looking at this graph, is all real numbers. We can put anything we want in place of x and it always works. But the range, you only get two values back. You're only allowed to use -2 or +2 and nothing else. And maybe as a last part of this question, is this a function? Clearly not. I mean, if you, let's say, chose this x value of +2 or this x value of -3, at -3, you get 2 and you get -2 back. I mean, that can't happen in a function. You can't have -3 going to 2 and -3 going to -2. I mean, the second you have one x value that goes to two different y values, it is not a function. So it's not a function. You can't write this thing as f of x is equal to, but we have a graph of it. For this last example, example 3, it's just really some practice using function notation. So here I'm giving you 3 points, but I'm writing them as f of an x value is equal to a y value. So this is f of -3 is equal to 1. We have f of 4 is equal to -2. And also f of 1 is 0. I'll write what those points are around it. So for -3 to 1, that's the point -3 for x and 1 for y. So I'll actually place that over on my axes. So that's going to be 3 places to the left and up 1. So -3, 1. For f of 4 is equal to -2, this one is 4, -2. So that means we go 4 places to the right, and we go down 2 places to 4, -2. And lastly, we have 1 for x, and we have 0 for y. So that is at 1, 0. Okay, now that we have this function graph, and it clearly is a function for each of the x values, it's only corresponding to one y value. I put a couple of equations up here, again, just to get some practice for how this notation works. So I want to start with this one here. F of x plus 1 is equal to -2. The idea is, can you think of the x value that makes this a true statement? So when I look at this expression, I'm thinking about this -2 as a y value. And actually, it's referring to this point located here. So here's my y value of -2. And once I determine my y value, I have to think of, okay, well, what goes inside the function to take me to -2? And in this case, that x value is 4. Again, just to reiterate, it has to be 4 when simplified is equal to -2. But here, I'm putting something strange inside the function. I'm calling it not just x, I'm calling it x plus 1. I mean, ultimately, the goal would be, if this thing could simplify to 4, I know that it would make this a true statement. So what I'm going to do is say, well, x plus 1, if that thing actually is the same thing as 4, I know it would take me to -2. This is a very simple equation to solve. I can subtract 1 from both sides, and I get x is equal to 3, which is the solution to this equation. If you want to check that this is true, you could take the original equation in place of the x, put a 3, and ask yourself if f of 3 plus 1 is equal to -2. I know that it's true because 3 plus 1 simplifies to 4, and f of 4 was defined to be -2. So for the second equation, so this one here, f of 0.5x is equal to 0. Again, I'm thinking of that 0 first, and that is referring to this point. Like here we have a y value of 0. And the question is, what do I put in place of x so that it takes me to 0? Scroll down a little bit for that. So, okay, I want f of 0.5 times x to be equal to 0. And I'm thinking about this portion of the graph. I know if x takes on a value, or actually if the whole thing in the rectangle takes on a value of 1, then f of 1 gives me 0 back. So I'm going to set up a new equation. I'm going to say 0.5 times x is 1. If 1 goes into the function, then I've solved this equation. To solve for the actual value of x, I can divide both sides by a half. So I have the 0.5's cancel, and 1 divided by the half is the same thing as multiplying by 2, and this is 2. If I want to check to see if this is true, it's very easy to do for this particular equation. You can say, okay, I'm putting 2 in place of x. And I'm asking if the result's going to give me 0 in this function. Well, 0.5 times 2 simplifies to 1, and we defined 1 to take me to 0, and that solves this equation.